Okay, let's jump right in. If you're an engineering student and you've got exams coming up, this is for you. We are going to cut right through all the hype and get straight to the core mechanics of blockchain. Everything you need to know to absolutely ace that test. So here's our game plan. We're going to build this thing from the ground up. We'll start with the 8 foundational properties, then we'll zoom right into the guts of a single block. From there, we'll look at how those blocks are actually chained together, we'll compare public and private networks, and then we'll wrap it all up with a super fast cheat sheet with all the critical points. All right, first things first, let's take that 10,000-foot view. Before we start taking the engine apart, we have to understand what makes the car go in the first place. These 8 properties, they're basically the DNA of any blockchain. They define what it is and, honestly, what makes it so revolutionary. Property number 1, and you could argue it's the most important one, decentralization. Put simply, it just means there's no boss, no central server, no single company in control. It's a peer-to-peer network where all the computers, the nodes, communicate as equals. A perfect example? Sending crypto to a friend halfway across the world without ever needing a bank to say, okay. Next up, immutability. This one's huge. It means once something is written to the blockchain, it's basically set in stone. You can't change it, you can't delete it. It's secured using something called cryptographic hashing, which acts like a unique digital fingerprint. Each block's fingerprint is linked to the one before it, making a chain that's almost impossible to tamper with. Think about a government creating a permanent, unforgeable record of who owns which piece of land. Then we have transparency. Now, on a public blockchain, every single transaction is right there on the shared ledger for everyone to see. It doesn't mean your name is attached to it, the addresses are pseudonymous, but the flow of transactions itself is wide open. It builds a ton of trust. Imagine a public voting system where you, or any citizen, could go in and verify the final vote count for themselves. Property 4 is security. And this isn't just one thing, it's more like layers of protection. You've got the heavy-duty cryptography, the decentralized structure we just talked about, and then you have consensus mechanisms, which we'll get to in a sec, that make sure everyone agrees on the truth. All these things working together make it incredibly difficult, almost computationally impossible, for anyone to create fake transactions. So that brings us right to consensus mechanisms. I mean, how do you get thousands of computers that have never met to all agree on something? Well, you use an algorithm like proof of work or proof of stake. These are the rules of the game that ensure every single computer on the network keeps an identical, valid copy of the ledger. And next, we've got smart contracts. The easiest way to think about these is as little if this, then that programs that live on the blockchain. They just run automatically when certain conditions are met, which means you don't need a middleman. For instance, an insurance policy could automatically pay a farmer the second a trusted weather service reports a drought in their area. No paperwork, no delays. Number 7 is scalability. And let me tell you, this is one of the biggest headaches in blockchain engineering. It's all about how well a network can handle a ton of transactions without slowing to a crawl. And there's this really tricky balancing act, because a lot of times, making it faster can mean making it a little less decentralized or secure. It's a classic trade-off. And finally, number 8, interoperability. Right now, a lot of blockchains are kind of like their own separate islands. They can't talk to each other. Interoperability is the quest to build bridges between them, to let them communicate and exchange data or assets. Imagine being able to take a digital sword you earned in one blockchain game and sell it on a marketplace that runs on a completely different blockchain. That's the goal. Okay, so we've got the big picture. Now let's pull out the microscope and zoom way, way in. We're going to deconstruct this single most fundamental piece of this whole puzzle, the block itself. So at its core, a block is just a container, right? It bundles like a bunch of transactions. But, and this is the important part, it also holds 2 other critical pieces of information, a hash of the previous block, and a special little number called a nonce. And as we're about to see, that nonce is the key to everything. Okay, pay attention, because this part is pure exam gold, the block header. It has 6 main components. First, the version number, which just tells you the rules for this block. Then, the previous block hash, that's the cryptographic superglue connecting this block to the last one. Next, the Merkle root. This thing is really clever. It summarizes all the transactions in the block into one single hash, super efficient. Then you have the timestamp, of course. And finally, the last 2 that work as a team, the difficulty target and the nonce. These 2 are the heart of the mining process. So we've seen the ingredients, now let's see how the sausage is made. This is where we get into forging the chain itself, the whole process of hashes, nonces, and mining. This is how that secure, unchangeable link is actually created. All right, if you remember one thing from this whole explainer, make it this. I practically guarantee this will be an exam question. What's the difference between a block hash and the previous block hash? The previous block hash is data inside the current block's header. It's the pointer looking backward. But the block hash is the unique fingerprint for the current block. It's generated from its own header. So one creates the chain and the other secures the integrity of the block you're looking at. Nailed that distinction. So how do they find that new block hash? Well, that's mining. In a proof-of-work system, miners grab a bunch of transactions and then they just start guessing. They pick a random number, that's the nonce, and they hash the block header with it. Then they check, does the result meet the network's difficulty target? If it doesn't, they change the nonce and try again, and again, and again, billions of times a second. The nonce is literally the missing piece of the puzzle they're racing to find to validate the block. Okay, deep breath. Let's zoom back out. We know how the blocks are built. We know how they're linked. Now let's talk about the two main environments they live in, public networks and private networks. The difference really boils down to one word, permission. A public blockchain like Bitcoin or Ethereum is permissionless. Anyone can join, anyone can participate. A private blockchain, though, is permissioned. You need an invitation. This one difference changes everything. Consensus on a public chain has to be completely trustless, whereas a private one can be managed by a few trusted members. Transparency goes from being super high in public to limited and private. So you get cryptocurrencies on one side and private supply chain networks for big companies on the other. We are in the home stretch now, so here it is, your final exam cheat sheet. These are the absolute most critical takeaways you need to have locked and loaded. Let's recap this fast. The 8 properties, that's the why. It's the whole reason blockchain is designed the way it is. The block header's 6 fields, that's the what, the actual components of each link. The previous block hash, that's the how. It's what literally creates the chain. The nonce in mining, that's the puzzle piece that miners have to find to secure a block. And finally, public versus private, the key is the permission model. It's all about who gets to play the game. So there you have it, the core mechanics totally deconstructed. But I want to leave you with one final question to think about. Now that you actually get the components, the nuts and bolts, what's next? What kind of new decentralized systems could someone like you, an engineer, go out and build with this stuff?